So we have the following sort of picture. We have the vector space V, which has, oh, yes, this screen here. Okay, it'll show up in a second. So we have the vector space V, and it has those 10 properties. And we also know that we can always write it as the span of some set of vectors. And if it's written as a span, just any span of S will have those 10 properties. So because you can take any vector space and write as a span, you know, it's like, or you take any span, it's going to be a vector space, and it's going to have those 10 properties. Or you take any vector space, there's going to be some set S you can write as a span. Okay, well, these set S's we were investigating last time, and there's a special property of this set S, which is linear independence. Okay, and we also mentioned that just in at the very end, that if V equals the span of S and S is composed of linearly independent vectors, if these two things are true, then S, so if these are true, if the set S, if the span of S is the whole vector space, we say S spans the space. And if S is composed of linearly independent vectors, if those two things hold, right, 1, 2, then S is a basis. So the definition of a basis is just a set S that spans the space and is composed of linearly independent vectors. And since it turns out that this, since any basis that sort of as a you can show that any basis for a given vector space has a fixed, well, not that a fixed, it has the same number of vectors. So if you found one set S1 that was a basis, you found another basis S2, those would each have the same number of vectors. They'll be completely different vectors, but they'll be the same number. That number, just the number of vectors in a basis, is called the dimension of V. So the dimension is a property of the space spanned by the set S. You figure, but so by a basis. So you figure out, you can discover what the dimension of V is by finding how many vectors are in the basis. But since the number of vectors is independent of the particular basis you found, it's a property of the space as a whole, because it doesn't matter which basis you found. So you say, that's why you say it's the dimension of V. And there's some common, for example, let's look at an example of this. or some examples. Let's look at RCN. Well, what is that space? Well, we can say that is the space. I'm going to, instead of N, I'm going to use a special case of 3 so we don't have to make the notation cumbersome. X, Y, and Z such that X, Y, and Z are any real numbers. Okay? This is what we mean by, this is the set on which the 3 component column vectors, we know that that forms a vector space. And we can immediately write this as, do the thing we normally do and write X times 1, 0, 0, plus Y times 0, 1, 0, plus Z times 0, 0, 1, such that X, Y, and Z are any real numbers. Now, what we've done here in this is we've rewritten, this is the definition of what, this is sort of a definition, but we've rewritten it as explicit span. So we can write this as the span of 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so it's clear that these 3 vectors are linearly independent, right? Because if I take any combination of these, you know, my test for linear independence says, okay, I take a linear combination of these. That's a 0 there. And set it to the 0 vector. Well, you can see, because the first equation is just A plus 0 equals 0, so A is 0. The second row is 0 plus B plus 0 equals 0, so B is 0. And the third row is 0 plus A times 0 plus B times 0 plus C times 1 equals 0, so C is 0. So transparently, this set S, we'll call it because it spans the space because of this explicit rewrite and because it's clearly linearly independent. We can write this as we'll call it the basis B is the set 1, 0, 0, 1, 0, 0, and 0, 0, 1. Okay, so this is called the canonical or standard basis. Standard basis for RC3. And you can see that it really didn't depend on there just being 3 vectors. I could have any number of vectors. And we give names to this. This is E1, E2, E3. Okay, so this, and you can see then that the dimension of RC3 equals 3. And that in general, the dimension of RCN equals n, the number of components in the vector. So said like that, it sort of doesn't seem surprising. So part of this is just notation. We can say that B for R to the n is equal to the set E1. If we write this, we'll write little half arrowheads over the vectors, over the symbols to indicate that they're vectors, E1, E2, E3, ... En. Well, you can see that E3 has a 1 in the 3rd row and 0s everywhere else. Just like if you had an E10, it would have a 1 in the 10th row and 0s everywhere else. Shruti.
So this, going back, when we were talking about the span and regular, which example was an explicit?
Okay, so that this is the linear independence test,
yeah,
which is you assume this and you have to show that this applies that A equals B equals C equals 0, and you can see just transparently here because like each vector has zeros in the other components, and there's no way to play off one of these against the other. Now, if I was to look at the image, at the correspondence of in E3, which is the Euclidean space with X, Y, and Z coordinate axes, then you know that you would have triples of numbers, like X, Y, and Z, and the length one vector, the length one sort of vector here, which you'd usually write this, we're writing it as 1, 0, 0, and usually you give this the name of I hat, right? So you'd have, so that for 3 dimensions, our E1, E2, E3, we could say in this case, we have that I hat corresponds to E1, and J hat corresponds to E2, and K hat corresponds to E3. And this isn't important if you haven't seen this before, but if you've had physics or engineering, that you'll be aware of these as unit vectors in coordinate directions. But what you really have is you have a vector space at the origin here, and these unit vectors. Well, actually, they're actually unit vectors, but the unit vectors are a standard basis for the vector space, and they're also then the sort of the way of writing any vector or any point. You're thinking of them as location vectors in this Euclidean space here, which is our space-time, or our space rather. Okay, so there's a connection here, but that's why these are the standard or canonical basis for R3. So we could have a separate problem. But so that was sort of straightforward. There's 2 different kinds of problems we could go from there that are more interesting. I can give you a set S, say of 1, 1, 1, say 2, 0, 1, and 1, 0, 2, and ask, is this set a basis? It's not the standard basis, but it still might be 3 vectors that span the space and they're linearly independent. So we have to check if the question was, is S a basis? Is S a basis of RC3? Then that's a kind of problem that we're sort of the standard problem that sort of indicates, if you can solve it, that you sort of understand all the concepts. So, and this is the kind of thing that appears on the rig exercises. It'll appear in a concept check, sort of aspects of this. And then this is sort of problem 1. The second problem is when you have subspaces of RC3, which are given because you have a linear system. Say you have some constraints that you've solved, and so you have some subspace that's in R3C, and then you have to ask, well, that's going to be a basis if the system's homogeneous. So we can ask, is a given, let's find a basis, or let's, if I give you some vectors, are these vectors, are they a basis of some space, which is a subspace, say, of the whole RC3? So that's the second problem. So we can ask, this is this first problem, which is maybe simpler conceptually, because you can ask, but you have to sort of, you can get the ideas down at this level. So let me pause here.